In this video, we're going to look at the different types of environments that create metamorphic rocks. Just like for sedimentary rocks, the environment is really important because that tells us what agents of metamorphism are at play and what kind of rocks you're going to get out of them. So the first environment creates what we call contact or thermal metamorphism. In this case, you have an igneous intrusion that heats surrounding rocks. So you can see here, there was that layers of shale, limestone, sandstone, and more shale all piled up. Magma intrudes into it. This is going to make maybe a stalk, maybe a edge of a batholith. But those heat up those rocks. When you heat up limestone, it makes a marble. When you heat up sandstone, it makes a quartzite. And shale makes a rock called hornfels. So that's another type of metamorphic rock, but it tends to be more of a kind of a catch-all term, so we don't use it too much in class. So in this case, the agents of metamorphism that are important are obviously really high heat, and because intrusions have lots of fluids, you also have high fluids. But there's very little extra pressure, so pressure really isn't a key here. So in this case, you're likely to not have any foliated rocks. Now, when rocks are altered by hot solutions, those hydrothermal fluids, this is often called a skarn. So if you see here, you have, this is from Superior, Arizona, where limestone has been heated, and it makes marble. You also get minerals like sphalerite, which is a zinc mineral, a zinc sulfide, garnet, and pyrite. Pyrite's an iron sulfide. These are actually really important here for Arizona because it creates important economic minerals like copper, or in a lot of cases like gold as well. This also happens at mid-ocean ridges some, but we're going to look at those mid-ocean ridges a little bit closer here in a bit. You can have burial metamorphism. This occurs in a subsiding sedimentary basin. Subsiding means the bottom of the basin is dropping. Just like the Gulf of Mexico. The Gulf of Mexico is a beautiful example of a subsiding sedimentary basin right now. So in this case, it's really just the weight of the rocks around it that are causing metamorphism. Obviously, unless you bury it really, really deep, you're not going to have that much pressure. So in this case, you get moderate pressure and moderate heat, but actually very little fluids acting on here. This creates mostly low-grade metamorphism. In dynamic metamorphism, rocks are going to deform as a consequence of shearing, but without an increase in temperature and pressure. This creates mostly along faults. So you can see up at the surface, if you have a fault, it creates breccia. It's called fault breccia, big angular pieces. But as you get a little bit deeper, things are able to flow a little bit better. And so instead of just breaking, the rocks actually sort of smear. So on the left is an example of a fault breccia. This is, I believe, Death Valley. On the right, this is a myelinite. So myelinite is a rock in which large crystals are replaced by smaller ones. So in this case, the crystals actually get smaller, and they look all smeared out. One beautiful place to find this is in a metamorphic core complex. So in this case, you have the rocks that are to become the McDowell Mountains, and you have the rocks that are to become South Mountain. So what happens is you get this big fault and things are pulled apart along this nice long fault. And what that happens is now you get South Mountain here. You get something like the McDowells over here. But because that little zone there has been smeared along that fault, this is called a detachment fault. We're going to get in those pretty quick. But it's been smeared that whole way. You actually get those weird myelinites the whole way on top of this little mountain system. That's actually just what South Mountain here is in the south part of the valley. The metamorphic core complexes are pretty common throughout southern Arizona. The Catalinas in Tucson are an example as well. And these are really interesting for structural geologists to study. In dynamothermal or regional metamorphism, metamorphism occurs because two continents collide. So this is a continent-continent convergent plate boundary where the two continents run into each other and you end up with lovely giant mountains just like the Himalayas. So this is going to occur over a really large area, which is why it's also called regional metamorphism, because it occurs over such a large area. In this case, we're going to increase the heat due to the geothermal gradient. We're going to increase pressure from that thickening crust. We're going to increase stress, so differential stress, just from the squeezing and the compression of the rocks around it. But you're not likely to get very large increases in fluids in this case. The highest grade metamorphic rock is in the very center of the mountains, where it's labeled the region of intense metamorphism. I actually worked with a geologist. She was a geochemist. At the time, she was at Oklahoma State University. She's now at the University of Texas. But she studies the formation of the Himalayas, and what she wants to know is exactly how they were put together. Which sections crumpled first, which got put on top of the other first. And she actually studies the chemistry of the rocks, particularly looking at the type of minerals that are there. Because when she knows exactly what temperature and pressure minerals form at, so she can tell the order in which the Himalayas form, looking at this regional metamorphism on a really big scale, which is pretty incredible. There's that same picture you've seen before, so you can see based on what rocks you find, whether it's gneiss, which is really high grade, or slate, which is really low grade, you could tell just how far into that mountain system you are. Hydrothermal metamorphism occurs where seawater is heated at mid-ocean ridges. These mid-ocean ridges have lots and lots of little faults, so cold seawater goes down those faults and those cracks, gets heated by the magma chamber that's under here. That magma forms due to lowering the pressure. So that's decompression melting, causes magma to form there at the crust magma boundary. The cold seawater gets down under there, gets warmed up, picks up all sorts of minerals as it goes, and then shoots back out in what's called black smoker deposits. You can see here. There's actually thriving ecosystems that live off of these. You can see in the picture there on the bottom left, there's tube worms and all sorts of stuff living around these black smoker deposits. Interestingly enough, these were first discovered by oceanographer Robert Ballard back in like the 90s, maybe late 80s, looking at the bottom of the ocean floor. Until he found these, we didn't even know they existed. And there's these huge thriving ecosystems that go on at the bottom of the ocean where no sunlight reaches. So rather than undergoing photosynthesis like we're used to with most small plants and animals, these actually undergo chemosynthesis, and they live off of the chemicals and that minerals that are dissolved in the hot water. Robert Ballard is probably best known, though. He's the guy who found the Titanic. So in the case of hydrothermal metamorphism, you have high heat, obviously, and lots of fluids, but very little increase in pressure at all. We have subduction zone metamorphism. In subduction zone metamorphism, we actually could form the rock blue schist. Looks like this. It's a schist that's actually blue. It has a type of blue amphibole, often called glaucophane, which is a really cool kind of dusty blue color. These rocks form in a very, very specific environment. In these subduction zones, you get an increase in pressure as that subducting plate gets shoved under, particularly at the accretionary wedge. But the ocean crust actually remains really cold. So you have an amazing increase in pressure, but not in temperature, which is kind of interesting. And so that's why this is the only place you can get a blue schist. This particular blue schist you see is actually from Oakland, California, because Oakland used to be a subduction zone, but it's obviously not anymore. Now, one of my favorite types of metamorphism is shock metamorphism. This occurs during a giant asteroid or some sort of bolide impact. Changes in the rock occur because of the shock wave created by the impact. And in this case, you're going to have the highest heat, which is high enough to vaporize a rock, and the highest pressures that occur at the Earth's surface when this thing actually makes contact. And one of the ways we know this happens is thanks to these rocks right here. So on the left, this is a sandstone. Your main cementing agent for the sandstone is silica. So these big blobs are quartz. So you've got big blobs held together by little blobs of quartz. So beautiful quartz arenite. You can see they're just blobs. Quartz doesn't have any cleavage at all. But if you hit it hard enough, you can actually start to shatter that 3D silicate structure. Under high pressures, you get this mineral over here. This is a shocked quartz called coesite. So it's been hit, so you form coesite. But if you hit it even harder, you get a mineral called stishovite. So this is actually a crystal of quartz down here that's been hit so hard that it's shattered into these actually very planar surfaces. That is not normal and only happens under really, really high pressures. Now, coesite and stishovite were both first discovered and recorded here in Arizona up at Meteor Crater.